Password here. I have to connect to this. Huh? It's not connected. No. I don't know where it is. No. Okay. 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 Good morning. First, I would like to thank the organizers. In this talk, I will talk a lot about localization, but I'm sorry, I don't will talk about many localization. So. But I'll talk about here about a very simple problem with very simple ideas, but with interesting results, at least for me. I hope that you enjoyed it. The title of the talk is Dirac wave transmission in Lévy-disordered systems. It's the same title of this recent paper that I published in collaboration with Luis Felipe Pereira, who is a professor here in the physics department of the Federal University of Rio Grande do Norte here in Natal, and with Anderson Barbosa, who is a professor with me in UFRP in Recife. So basically, here I will discuss about this paper specifically. The talk is organized, as can be seen here. First, we'll talk about waves in disordered media. Basically, we understand the main difference between a Lévy-type disorder and a typical disorder. And we compare the Anderson localization and the anomalous localization, and then we will discuss specifically the problem here, where we study Dirac waves in Lévy-type disorder. In order to connect our results with experiments, we discussed, we investigated the electronic transport in graphene. So we'll talk a little bit about graphene and the transfer matrix method, that is the method that used to solve the problem, and then we discuss the results. Okay, one of the most celebrated factors of waves in random media is the Anderson localization, which is characterized by a complete suppression of wave diffusion due to destructive quantum interference, leading to exponentially localized aging functions. But this standard localization, the Anderson localization, appears when the disordered models involve distributions with finite mean values, which we say that when it happens, we say that we have a standard disordered system. But in contrast, when the probability density of the disordered distribution has a long tail, we observe an anomalous localization, as occurs in the case of a Lévy distribution, in which the probability density has a power law tail, which is given by this for large values of x, where x is the random variable here. And if this coefficient alpha is between 0 and 1, the first and second moments of the distribution diverge because of half tails, while for alpha between 1 and 2, only the second moment diverges. Here you have a comparison between the typical disorder and Lévy-type disorder. Here you have the Lévy disorder, Lévy distribution, with alpha equal 1/2. We have only analytical expression for this distribution for this value of alpha. You can see here in this red line that we have this long tail here. And here in the blue line here you have the very known normal distribution. And here we have a common, a usual example how to compare these two systems is in the random walk. Here you have the Anomalous random walk, and here you have the Lévy random walk. We can see here that due to this long tail, we have the appearance of these very long steps here in the Lévy case. And these long steps make the dominant contribution to the transport. And you can see clearly that in the Lévy case, in comparison to the normal case, we have a smaller density of disorder, and also large fluctuations. Okay. And if you consider a Schrödinger electronic wave submitted to a typical one-dimensional disorder, it shows standard localization, which means that the average transmission decays exponentially with the system length L. We have this, where this L here is the Freeman path, and the logarithm of the increases linearly with L. So these two behaviors here characterize the Anderson localization when you have a electronic wave submitted to a typical one-dimensional disorder. But when you have a Lévy type disorder, the average transmission decays as a power law of L, where this L here is the system length, and the logarithm of T increases as a power law of L. So we have this behavior for the case of a Lévy type disorder. We can see here that the localization, the Anderson localization, is stronger because in the standard case, the transmission decays faster than the Lévy case. Okay, Lévy type distributions have been considered in the study of various problems related to different scientific areas. So there's a plenty of works studying this. Lévy disorder in biology, economy, chemistry, mathematics, and also various branches of physics. Another topic of intense research interest is in the last years, the investigation of Dirac waves in typical disordered media. It can be attested by the great number of works addressed to the study of the electronic transport in disordered graphene. Some of you are experts in this topic, so there's a lot of work in Dirac materials, in disordered Dirac materials, right? But after these studies, an issue remained open. What type of localization will manifest in the case of Dirac electronic waves subject to a Lévy type disorder? In all these studies, a Dirac wave was not considered. So if you have a Dirac electronic wave in a Lévy type disorder, what type of localization will manifest? And here we address this problem. In order to connect our results with experiments, we investigate the electronic transport in a disordered graphene. Basically, you have a graphene superlets with potential barriers. We have two regions, one with the potential equal V, another with the potential equal to 0. And these two regions alternate. And the width of each region follows a Lévy distribution. Okay? It's a very simple problem. And let's see the rest. Okay. First, we will discuss a little bit about graphene. Graphene is an atomically thin layer made out of carbon atoms arranged in an hexagonal structure. It has two atoms per unit cell, which defines two sublattices, the sublattice A and B. In the reciprocal lattice, you have these two very important points that is called the Dirac points, the K and K prime. In the dispersion relation can be obtained, and it's given by this. It's derived from the tight binding model, considering only hope to nearest neighbors. And if you expand this dispersion relation in the vicinity of the Dirac points, we obtain this linear relation between the energy and the moment, where this Vf is the Fermi velocity and Q is the momentum measured from the Dirac point. And if you remember, in the relativistic energy is given by this. If you put the mass equal to 0, you have a linear relation between the energy and the moment, very similar to this. The only difference is here in graphene you have the Fermi velocity instead of the light velocity. So in fact, we can describe the low energy electronic excitations graphene as massless Dirac fermions. And the effective Dirac equation for our system is given by this. Here you have the Pauli matrices, the Fermi velocity, and Vx is the potential, which is a piecewise constant, which is piecewise constants. In each region, it's constant. So here you have the spinor with two components, components A and B, which are related with the two graphene sublets, which we will call the pseudo spin. In order to solve the problem, we found the wave function in each region and used the transfer matrix method to connect the incident wave function with the wave function. So it's very simple. We have a matrix for each region, and if in our superlets we have any regions, you have the product of any matrices, and obtain this final matrices X. And from this matrix, we obtain the transmission coefficient. Okay? Okay. Let's talk about the resistors now. Okay. In our resistors obtained here, we consider that V, the potential, the height of the potential, is 50 millielectron volts. And the average was calculated from 10,000 ensemble visualizations. First, we consider the average of the transmission, and we calculate for two different values of the incidence energy. First for 20 millielectron volts and 30 millielectron volts. In the next slide, it will be clear why we chose these two values, right? This is a value that is smaller than half of the potential. It's a value that is larger than half of the potential. So each line here is a different value of the incidence angle, theta 0. And we consider that theta 0 varies from 0 to pi over 2 by 0.05 radians at each step. And for theta 0 equals 0, it's the first line here. We have that the average transmission is equal to 1. It's very well known in graphene that it's a consequence of decline tunneling. Basically, decline tunneling prevents the quasi-particles in graphene to be backscattering, prevents backscattering from normal incidence. So no matter the height of the barrier, the width, how they are distributed, the transmission will always be equal to 1. But for theta 0, larger than 0, we have this behavior here. So the transmission decays as a power law of L, where L is the length of the. So if you remember, this means that we have here an anomalous localization, which also occurs in the other problems, in the other systems. So until here, there's nothing special. Yeah, your alpha is this. Yeah, this alpha here. Yeah. Okay. Okay. We generate a sequence of numbers, and each number in this sequence of numbers follows a Lévy distribution with this specific value of alpha, and each number is the width of one region in our superlets. Okay. Yeah. So. Yeah, and so we obtain that the average transmission as a power law of L, which means that we have an anomalous localization, as in the Schrödinger case. Okay. But when we consider the logarithm of t, something different occurs here. We have 4 different values of the incidence energy, 20, 25, 26, and 30. For these two cases here, 20, 25, when the energy is smaller or equal to half of the potential, we have that the logarithm of t increases as a power law of L, which means anomalous localization. But when the energy is larger than half of V over 2, we observe a transition between this behavior to this behavior. And this behavior means anomalous localization. This behavior here means standard localization, right? So we can see here that the linear behavior of the logarithm of t appears when the energy is larger than half of the potential. You can see that this transition occurs for different values of theta zero depending on the energy. So what we did was to calculate specifically for each energy the angle where the transition occurs. So these are these red circles here. And you can see that the numerical resistance can be perfectly fitted by this function. And we call it a critical angle. So when the incidence angle is below this angle, we have an anomalous localization. When the incidence angle is above the critical angle, we have this standard localization. It's important to see here that the transmission, the average transmission always shows anomalous localization. The transition is only observed in the logarithm of t. It seems that they are not agreeing with each other, right? But here it was not the first time that it appears. I didn't mention it, but for the Schrödinger case, for alpha between 0 and 1, we have that average transmission will be proportional to L minus alpha, and the logarithm of t be proportional to L alpha. And for alpha larger or equal to 2, we no more have a Lévy distribution. We have the standard case, so the average of t will be proportional to the exponential of L and minus the logarithm of t will be proportional to L. But in this region here, when alpha is between 1 and 2, first transmission shows anomalous localization, but the logarithm shows standard localization. So this region is an intermediate region, the anomalous and the standard localization. And what we are seeing here is that without change the value of alpha, so we are not changing the alpha, we will not change our distribution. We still have the long steps. We still have the smaller density of this order. But even without changing alpha, we are seeing this transition from here to here. And it has never been observed before. Okay? It's a continuum model. No, it's the back scattering in the barriers, in the potential barriers. Okay, we are looking to only to one to 1 point. Okay. Okay, for normal incidence, there's no localization. But we are we are saying this for normal incidence, the client only prevents, but for incidence angles larger than 0, we have backscattering. We have okay. So okay, what we are saying is that even without a Lévy disorder, always we will never will find an Anderson localization here. It is. See, yes. Uh, so this T here will never be this, because this means under localization, this is standard, anomalous. Uh, okay. Okay, we have to yeah, yeah. We are only looked into to a single Dirac. The most simple problem. Right? Uh, because I'm expanding this because first we have if you expand this dispersion relation in the vicinity of k, we have an equation, and if you expand it in the vicinity of the order, we have a different equation. But in our problem, we have degeneracy. So no matter if you look to the k or k prime, the rest will be the same. We can break this degeneracy between what's called the valley. Yeah. Yeah, yeah. Okay. 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 Uh, Here we analyze the anomalous localization and the standard localization regions. Basically, we analyze here we have the standard localization region where we analyze for different values of the incidence angle and see that all the restes can be fitted only by power below decay. But here, when the energy is above is larger than the half of the potential, the logarithm of t depends linearly with the length, which is a characteristic of a standard localization. Here we analyze for different values of alpha. In fact, this behavior occurs always when the alpha is between 0 and 1. Okay, no matter the value of alpha, we always will have the same transition here in the behavior of the logarithm of t. Okay. And the last rest is where we analyze the transmission and standard deviation as a function of the energy. We can see two important things here is that in the transition, we see that the transmission decreases abruptly, and also its fluctuations. Okay, these two, and this reduction in the fluctuation is a characteristic of a transition between an anomalous to a standard localization, right? So we can see here that there's no fluctuations in the transmission for the standard localization region. So in order to understand this, we can analyze a simple problem that we can look for to a the transmission of a quasi-particle in graphene in a single barrier. Here you have an incidence angle theta and a transmission angle phi. And since the potential does not depend on the coordinate y, the component ky of the wave vector should be the same in all regions. So here you have ky and ky. But the component x takes two values, kx for the region where Vx is equal to 0, and Qx here, inside the barrier. And since the Ky is equal, we have this, which gives us this relation here. We can see that for when the energy is smaller than half of the potential, the incidence angle is larger than the transmission angle. For the energy equal to half of the potential, the transmission and the incidence angle are equal. And when the energy is larger than half of the potential, the incidence angle is smaller than the transmission angle. And there is a critical angle such that the quasi-particle is transmitted at 90 degrees. And if you replace the transmission angle by pi over 2, we have this critical angle, which is the same critical angle that separate the two localization regime. So for large angles, incidence angles larger than the critical angle, the x component of the wave vector becomes imaginary. So the incident plane wave became evanescent waves as they are being transmitted inside the barrier. So when the incidence angle is smaller than the critical angle, we have a plane wave outside the barrier and also a plane wave inside the barrier. But when the incidence angle is larger than the critical angle, inside the barrier we have an evanescent wave. And as a consequence of this, the transmission decreases abruptly, as we observed in our resistors. And this reduction in the transmission leads to a strong localization, a more strong localization of the quasi-particle, which we can use to explain this transition between an anomalous. Okay, I cannot say that we are really in a standard localization because the transmission is still showing a power law decay. But a transition occurs, not exactly from a standard, from anomalous to standard, right? Also, the reduction in transmission also reduces its fluctuations. Since the anomalous localization is a consequence of large transmission fluctuations, which appears in the systems with a Lévy type disorder. When these fluctuations are suppressed, the system stays in the standard localization regime. So, to summarize everything, first here we investigated the propagation of Dirac electronic waves in a system subject to a Lévy type disorder. We performed numerical calculations in a graphene with potential barriers. We show a transition from anomalous to standard localization. The phase diagram was obtained, and finally we attribute the transition localization regime to an abrupt decay in the transmission of the system, which occurs when the incidence angle is higher than a critical angle, and induces a decrease also in the transmission fluctuations. And we believe that our could be acquired in the following experiments in graphene superLEDs. And thank you for your attention. Yeah, okay, I have a one dimension